will post. I know you are going to have first test, right? Tonight is your first test. So I think your student will be busy studying for preparation for tonight's exam. But we have to move on. Okay. I will today we just want to discuss on the next chapter, which is Opamp, basics of operational amplifier, from chapter 10 of the book reference. Okay, let's continue. Okay. As usual, somebody, okay, Nurul Islam has started recording. Good. Okay. Okay. When we say operational amplifier, you will see this symbol. And Opamp is represented as a triangular shape device with two inputs and one output. So in terms of its functionality, the Opamp change voltage amplitude and also the polarity of the voltage. So the characteristics of Opamp, it has high gain, high impedance, infinity, and low output impedance. So the ability of the Opamp to amplify signals with very high impedance at the input side, but low impedance at the output side. So an Opamp can be used to make many circuits such as the oscillator, the filter, regulator, comparator, and many more. Into differentiator, integrator, so many other. The list can goes on. So today we just learn about the basics of Opamps. There are many kinds of Opamps produced, and Opamp is actually small circuits comprised. The Opamp itself is integrated circuit. The inside of the Opamp, it contains many transistor circuits. So the Opamp can be made of BJT circuit or FET circuit, depending on the Opamp. So we have like 741, LM322, LM, so many varieties of Opamp. But the commonly used an Opamp is 741 Opamp. So in this diagram, it shows the internal circuitry of an Opamp. For example, in this circuit, you have how many transistor in this circuit? 1, Q1, Q2, Q3, Q4, and then Q5 here, 6, 7, all together 17 here. 17 transistors inside an Opamp. A compact circuitry inside an Opamp. An Opamp can be 7 legs or 4 legs. This is the schematic diagram of a 741 Opamp. So a 741 Opamp internally has many BJT circuits. Okay, but the connection of the Opamp, you will only see a few legs of the Opamp that you are going to connect to make the Opamp functional. Okay, so despite of having so many transistors inside the Opamp, we can always simplify the application of the Opamp itself. So the symbol, as I mentioned just now, symbol for an Opamp is always a triangular with two inputs one input is labeled as negative, another input is labeled as positive. So the negative input is called the inverter. The input with label as plus sign is the non-inverting input. And the output is only one output. And to make this op-amp working, we need to apply bias voltage. And the bias voltage normally, two bias voltage, negative V and plus V. So depending on the voltage, based on the circuit diagram, circuit specific device sheet, you will have information regarding the safe working supply voltage. So here would be VCC for the BJT lah, inside the circuit. So normally for 741, maximum would be 15 volt. If I'm not from the data sheet, I think it will say negative 22 to negative plus 22, but normally we use 15 volt. Okay, as long as you do not use, you do not apply the voltage, biasing voltage higher than the safe voltage supply, the op-amp will be working normally in good condition. But if you apply slightly below, your op-amp can last long. But you cannot apply the VCC too low. It has to be in the range of the working range. So this is the symbol. And in the right side of the figure, you will have the schematic, not schematic, the actual representation where a 741 op-amp is actually a 4-leg compact IC, and the 4 legs in the left side, you have legs label 1, 2, 3, 4, and the right leg label 5 from bottom, 6, 7, 8 upwards. So for each of the leg, it represents the specific connection. For example, leg number 1 is for offset null, the inverting and the non-inverting inputs are for the leg 2 and 3. Leg number 4 is negative V bias voltage, and 7, leg number 7 is for the positive bias voltage. The output is measured at leg number 6, and leg number 5 and 1 are actually offset null. And leg numbers 8 and C means not connected. So leg number 8 is just open. It is there to make the circuit stable so that you have 4 in the left side, 4 in the right side. So when you attach the op-amp, it is stable. So kalau kaki 7 ni ada satu tergantung, maybe it not stable because of one leg is missing. So leg number 8 is just not connected, but it's there. So this is the op-amp appearance. One is symbol, one is actual schematic lah, outer surface schematic. Okay, for an op-amp, we will have, let's consider the single-ended input. Okay, an op-amp can amplify an input with the same polarity as the input signal. When you apply the non-inverting, when you apply the inverting input to the ground. So for example, when you apply the input to the non-inverting terminal, input terminal, the output will be same polarity. Same polarity means same phase. So if you when you give a positive phase of the input, the output will have a positive phase also. with amplitude that is depending on the gain of the amplifier. Okay, and if you apply V in at the inverting input terminal, the negative terminal, the output voltage will become out of phase by 180 degrees. So the amplified output with the opposite polarity as the input signal. So here you see when you apply your sine wave, positive first, negative, but the output will appear negative first, then positive phase. So this is say 180 degrees out of phase. Okay, so that is the difference between applying input to the inverting, non-inverting input will produce same polarity. But if you apply input to the inverting input terminal, your output will be out of phase. Okay, this is the basic theory. However, in reality, you will have to consider few normal conditions for Opamp. So let's consider, let's calculate the gain for the amplifier. A basic gain equation is always V out over V in. This is the common, the standard equation for gain. So if we have this Opamp not connected without any feedback loop to the input side, we will have an open loop gain AO multiplied by the input. The input of the Opamp will always be two inputs from negative terminal to the positive terminal, or from the non-inverting to the inverting terminal. Okay, so when you have input V in to the plus terminal, this would be 0. So the input is only coming from V in, because V negative here is 0, V plus with some values. So because this is 0, the difference between V plus and V minus is due to the value of V in only. So therefore, V out is actually the gain, open loop gain, AO, multiplied by V plus only, or V in, where V plus is having the value of V in. Okay, this is the condition when your inverting input terminal is grounded. Therefore, you will produce a gain equals to V out over V in, which is called A open loop gain. Okay, if you apply, you change the polarity, not polarity, you change the input. Now you apply input at the inverting input terminal, which is the V minus, and you ground the the input terminal, the inverting input terminal. So you have V plus is 0. Okay, so your V out now is equal to AO times the difference between V plus minus V minus V minus. So you will get a value of negative AO times V in. Now you see you have a negative sign in front of the equation. So then you will have your gain is equals to negative AO, because gain, although it's the value of VO over V in, now it becomes negative AO. So this is why we say negative means opposite. So this is only happen when you have your V plus connected to the ground. Okay, and you have you say when you apply V in to the inverting input terminal, you will produce a negative value. So from that, we mention this is the inverting input with a minus sign. For a amplifier, in reality, there should be some values between V negative and V positive here. So actually, the amplifier is amplifying the amount of voltage difference between the two input terminals. Okay, and if you apply V in here, so you would expect same voltage enter through the V minus and through the V plus. Okay, we have same input signals at both inputs. Both of the input terminals are equally amplified but in opposite polarity. These signals cancel out, making the output become zero. However, there will be very small output produced even though you have a common connection between the inverting and the non-inverting inputs of the op-amps. Okay, and it will produce differential and the common mode operation, whereby for an op-amp with arbitrary input voltage V1 and V2, there will be differential input signal Vd, and normally the value of V1 and V2 will be very small, few millivolt, but at the output you will have very small volt. Okay, and the V1, the difference between V1 and V2 at the input terminals will give differential input voltage, and the common input signal Vc is actually the average of the two input voltages at the input terminal. So Vc is the common mode is equals to average, which V1 plus V2 divided by 2. But at the output of the op-amp, Vo is going to be the voltage due to the differential input and also the voltage due to the common mode signal. So therefore, you will have Vo is the gain, differential gain, times the Vd plus the gain due to the common mode arrangement multiplied with the common mode voltage. Okay, and you will also have common mode rejection ratio for an op-amp, where common mode rejection ratio is actually the magnitude of the differential gain, or the ratio of differential gain to the common mode gain. So you will have AD divided with AC. That would be the common mode rejection ratio. And CMRR normally we refer as dB unit. So if you want to make it into dB, you have to 20 log dB lah. Okay, and the gain, the CMRR, simply ratio of AD to AC. Okay, the output voltage of the op-amp Vo is equals to the differential gain plus the common gain, the voltage due to the differential gain and the voltage due to the common mode. If you rearrange this equation, you will produce, it is going to be equals to AD times Vd multiplied by 1 plus 1 over the common mode rejection ratio multiplied with Vc over Vd. So if you are given data sheet and stated the common mode rejection ratio value, you can calculate your Vo if you have your differential gain, and you can test the performance of the op-amp. Okay, so basically, because CMRR is in the bottom of the equation, when CMRR is large, the output voltage will be influenced mostly by the differential signal. Okay, because of this VD, differential signal is the VD, while the effect of the common mode component is greatly reduced. Okay. The common mode rejection ratio, an op-amp has input voltage of VI equals to 150 microvolts and VI2 equals to 140 micro, between 120 to 140 and 150. The differential gain for this situation will be the difference between 150 minus 140 microvolts. So therefore, you will get about the differential gain. No, this is the gain. The gain is around 4,000. So the differential voltage will be 10 microvolts. So compare the output voltage with the component of differential input signals when the CMRR of the op-amp is 1,000 and 10,000. You can compare this one at 100 CMRR and at 10 to the power of 5 CMRR, it will be very large difference. And the CMRR indicates the op-amp's ability to reject a signal applied simultaneously to both inputs. The higher the CMRR, the better the op-amp. Typically, an op-amp with CMRR in the range between 80 to 120 dB is a good op-amp. CMRR, however, decrease when frequency increase because of the CMR is in the bottom of the equation. So it is actually inverting, or we can say inversely related to frequency. Okay, for an op-amp, because an op-amp consists of many transistors inside it, we can always evaluate an op-amp circuit by evaluating the AC equivalent of the transistors. So we can simply, despite of the many transistors inside the op-amp, we can always represent it as one circuit. Okay, and for example here, you will have you can convert differential gain at the input VD, so you will expect there will be V1, V2 at the input terminal, and Ri will be the internal resistance of the op-amp, and at the output side you will have the differential gain AD times VD, and you have RO, and you measure the output voltage VO across this. So from this figure, practically you have this arrangement of input and output of the circuit. But the ideal situation is actually you will have V differential here. The resistance at the input side will be very large because an op-amp characteristic has infinity impedance. So therefore, it is like an open circuit, and because of high input impedance. And at the output side, the RO is very small. So as if there is no resistance. So therefore, it makes your op-amp in the ideal situation is only represented as VD at the input and VO measured across this AD times VD. Okay, So the input signal applied between the input terminal, C is the impedance Ri, typically very large, infinity value, and the output voltage is shown to be the amplifier gain times the input signal taken through the output impedance Ro, typically very low, or we can assume like 0. And the ideal Opamp circuit would have infinite input impedance, 0 output impedance, and infinity voltage gain, very large gain. However, in practice, we cannot have infinity gain because of the bias voltage of the op-amp. You cannot produce amplification higher than the supplied voltage. So if you have your op-amp supplied with VCC negative 15 to 15 volts, definitely the output of the voltage of the op-amp cannot be more than 15 volts because it saturates at supply voltage, at the bias voltage. Okay. The op-amp gain, we can have two kinds of gain depending on the operating of the op-amp. We can have an open loop gain or we can have the closed loop gain. The open loop gain is the configuration where there is no feedback from the output to the input. In the open loop configuration, the gain can exceed to 10,000. But for the closed loop, the configuration reduce the gain very much because there will be feedback by connecting resistors to the input. In order to control the gain of an op-amp, it must have the feedback. And this feedback is a negative feedback. And the negative feedback reduces the gain and improves many characteristics of the op-amp. For the open loop, it can make the op-amp become unstable. So to avoid instability of the op-amp, we always use a closed loop connection for an op-amp. How to use the op-amp? We would like our op-amp to amplify the input signal by a factor of an arbitrary value. However, the open loop gain is fixed and it will be too large. We need to make the amplification system as the closed loop using some external circuit. And there are two configurations of using the external circuit. Whether we set the op-amp working in the non-inverting arrangement or in the inverting arrangement. Okay. If we consider the closed loop configuration, we will apply V input if we connect to the inverting input and we connect external resistor RF. We call it RF because this resistor is actually the feedback resistor from the output terminal feedback to the input terminal. So in this case, because the inverting input terminal is grounded, so V1 here, so V2 will be here, and this V2 is actually 0. So now you only see current pass through R1, RF, and you measure at VO. Okay, so for this closed loop configuration, we can sketch the AC equivalent circuit. We will have R1, Ri, and the RO in series with the AOL gain or open loop gain multiplied by the V in. Okay, and the RF is actually the resistor that is connected from the output to the input. So this will be the AC equivalent circuit for this simple closed loop arrangement. So the open loop gain AOL, Ri is input impedance, Ro is the output impedance. VO is measured as the value multiplication of A open loop times V in. Okay, and V in comes from the input terminals, the inverting input terminal. Since A open loop is large, we consider infinity gain. Vi is equals to Vo over the open loop gain. That would be, because this is a large value, so it will make Vi is almost zero value. But the principle of ideal situation of an op-amp, Vi is actually the difference between the inverting and the non-inverting input terminals. So Vi is actually V plus minus V minus. Because V plus is grounded, therefore V plus is equals to V minus and equals to 0. So it means that V minus is also grounded. Okay, this concept is called the virtual ground. So because you connect this Vi to the ground, so you will have a virtual ground to the other input terminal as well. So using KCL, so now nothing flow in the bottom, only current flow in the top path. Okay, so therefore, if you consider voltage drop across here, voltage drop across here, and voltage output. So V1 minus Vi divided with the R1, this is Kirchhoff's law, minus Vi divided with Ri is equals to Vi minus Vo divided with the Rf. Okay, because Vi is 0, therefore your V1 over R1 is then becomes value of negative Vo over Rf, and Vo over V1, which is the gain, because you want to consider output over the input, is actually a factor of Rf over R1. Okay, so there is no need for you to know the actual value of Ri. So the voltage gain now is simply equals to Rf over R1 with a negative sign, because you apply V1, V in you, at the inverting input terminal. So you have the gain is a negative gain. Okay, and the circuit provides a voltage gain with a 180 degrees phase inversion from the input signals. Okay, you can use to solve for this one, you can use the superposition theorem. Apply your circuit theory 2 to solve for the equation. But basically, when you connect your op-amp with the arrangement that the input is applied to the negative input terminal, you will have inverting amplifier, where the inverting amplifier gain is always AV is equals to negative Rf divided with R1. So in other words, you can estimate the gain of the op-amp by only using the external resistor divided with the resistor that is connected to the input terminal. Okay, the golden rules for op-amp is always two basic rules. Number one, there will be no difference. So in other words, voltage difference between the input terminals must be 0. When you have V1, V2, the difference will be 0. Okay, the input draws no current. So meaning that there is no current flow into the inverting input terminal and to the non-inverting input terminal. Okay, and with that arrangement, you can make the op-amp into inverting amplifier or non-inverting amplifier, summing amplifier, unity follower, integrator, differentiator, comparator pun boleh. So ada many other arrangement. Okay. Before we go with the specific arrangement, I stop here. I want to show some videos on basics of the op-amp. Let me show you some video. So I have to unshare first, then I open. Okay, this one. I want to share my share content. Include computer sound. Okay, let us see some videos. I haven't have time to. Can you listen the sound? Dengar suara tak? Suara daripada video tu.
Dengar.
Dengar.
Okay, good. So I play.
Hey friends, welcome to the YouTube channel all about electronics. So in this video, we are going to talk about the basics of the operational amplifier. And in the upcoming videos, we will talk more about this operational amplifier and we will see how we can design the different circuits using this operational amplifier. So as its name suggests, this op-amp is basically a amplifier and the basic job of any amplifier is to amplify the input signal. Now let us understand why it is known as the operational amplifier. So in early days when digital computers were not evolved, at that time the different mathematical functions like addition, subtraction, integration and differentiation were performed using this operational amplifier. So just by connecting a few resistors and capacitor, it is possible to perform different mathematical operations. And that is why this amplifier is known as the operational amplifier. So now if you see the circuit symbol of operational amplifier, it can be represented by this symbol. So it consists of two inputs and one output. And most of the amplifiers consist of a two power supply, the positive and the negative power supply. But there are many op-amp ICs which runs on the single power supply. So now in this operational amplifier, the input terminal which is marked by this positive sign is known as the non-inverting input terminal, and the another input terminal which is marked by this negative sign is known as the inverting input terminal. And it will be get clear to you very shortly why it is known as the non-inverting as well as the inverting input terminals. So now if you see this operational amplifier, it is a one kind of differential amplifier with a single output. It means that this amplifier amplifies the difference between the two input signals. So let's say V1 and V2 are the input signals which is being applied to this operational amplifier, and let's say the gain of this operational amplifier is A, then the output will be equal to A times the V1 minus V2. So let's say if we have applied the single input to this operational amplifier and we have grounded the another input terminal, then at the output you will get a times V1, where A is the open loop gain of this operational amplifier. The reason it is being known as the open loop gain because it is the gain of the operational amplifier when there is a no feedback from the output to the input side. So suppose if you are applying the sinusoidal signal over here, then at the output that sinusoidal signal should be get multiplied by the factor of this gain, and at the output you should get a amplified sinusoidal signal. Now here the phase of this output voltage will be the same as the input voltage. Likewise, whenever we are applying a input to this negative terminal and we are grounding the another terminal, then the output of this amplifier will be equal to minus A times the V2, because the difference between these two input terminal will be equal to 0 minus V2, that is equal to minus V2. So suppose let's say if we are applying the sinusoidal signal at the input, then at the output we will get the amplified sinusoidal signal which is having a 180-degree phase with respect to input signal. That means the output will be get inverted by a 180-degree, and that is why this input terminal is known as the inverting terminal, because the output will be get inverted with respect to input. So now here suppose if we apply the input signal between these two positive and the negative terminals, then at the output we will get a times this differential input signal, where here this A represents the open loop gain of this operational amplifier. Now this operational amplifier is very high gain amplifier, and the value of gain used to be in the range of 10 to the power 5 to the 10 to the power 6. So let's say even if we apply the 1 millivolt of signal between these two terminals, and let's say if the gain of this op-amp is 10 to the power 5, then at the output theoretically we should get 1 millivolt signal that is multiplied by the 10 to the power 5, that is equal to 100 volt. Or let's say if we apply 1 volt of signal, then theoretically we should get a output as a 10 to the power 5 volt, but that is not possible, and the output of this op-amp is restricted by the biasing voltages that is being applied to this op-amp. So the output voltage will be between this biasing voltages. So if you see the voltage transfer curve of op-amp, then it will look like this. So here the x-axis represents the differential input that is being applied to this operation amplifier, and the y-axis represents the output voltage of the amplifier, and here the slope basically represents the gain of the amplifier, which used to be in the range of 10 to the power 5 to the 10 to the power 6. Now here let's say the gain of the op-amp is 10 to the power 6, and let's say we are applying a 1 microvolt of signal, then at the output we should get a 1 volt of signal. Likewise, let's say if we apply 10 microvolt of signal, then at the output we will get a 10 volt of output. But as we increase this input signal, then you will find that after some value of input signal, the output will be get saturated to the value plus Vset, which used to be less than the positive biasing supply. So in this way, as soon as the input voltage goes beyond some certain value, the output will be get saturated to the plus saturation voltage, and same is true for the negative input voltages. So as soon as the input voltage goes beyond some threshold value, at the output you will get a minus saturation voltage. So whenever this operational amplifier is used in an open loop configuration, that means there is a no feedback from output to the input side at that time. Even if we apply a small input signal between these two input terminals, then also you will find that the output will be get saturated towards the positive or the negative biasing voltages. So this particular characteristic of the op-amp is particularly useful when we use this op-amp as a comparator. So this is one of the application in which this op-amp can be used. But if you see this op-amp can be also be used in so many other applications, like in designing the active filters, oscillators, waveform converters, and analog to digital and digital to analog converters. And if we count the list will go on. So basically this op-amp is very versatile IC, and you will find this op-amp in so many applications. Now the reason this op-amp is used in so many applications is because of its different characteristic. So let us see the different characteristic of the op-amp because of which it is being so versatile and used in different applications. So before we see that, let us see the equivalent circuit of the op-amp. So as you can see here, this Ri is the input impedance of this op-amp. Likewise, this Ro represents the output impedance of this op-amp, and the output voltage of the op-amp will be the open loop gain multiplied by the difference between the input signals V1 and V2. So now before we see the different characteristic of the op-amp, let us see the different characteristic of the ideal op-amp. So the ideal op-amp should have this input impedance Ri that is equal to infinity, so that whatever input that is being applied between the input terminals will directly get applied to the op-amp. Similarly, the output impedance of this op-amp should be equal to 0. That means whenever we are applying the output load to this op-amp, then the output voltage should directly come across this output load. Then if you see the bandwidth of the ideal op-amp, the bandwidth of the ideal op-amp should also be equal to infinity. It means it should support all the frequencies starting from the 0 Hz up to the infinite. Similarly, the gain of the ideal op-amp should also be equal to infinite. Apart from that, whenever these two input terminals are 0, that means the input to this op-amp is 0. At that time, the output of this ideal op-amp should be equal to 0. Now, apart from these characteristics, there are few more characteristics of the ideal op-amp, that is slew rate and the common mode rejection ratio. So we will see more about these different characteristic in detail in separate videos, but let us see the basics of this different characteristic. So in a simple way, if I say the slew rate is basically how fast the op-amp is able to reach its final value, and that is particularly useful when we are applying a square wave to the op-amp. So let's say we have applied the square wave to the input of this op-amp, and at the output we are getting this output waveform that is varying from 0 volt to the V saturation. So the ideal op-amp should be able to reach from the 0 volt to the V set volt in a 0 time. So for the ideal op-amp, the slew rate should be equal to infinity. Generally, the slew rate is defined in a unit of volt per microsecond. That means how fast the op-amp is able to respond to the output voltage. Then there is another parameter which is known as the common mode rejection ratio. So let us understand very briefly what do we mean by this common mode rejection ratio. We will talk more about it in a separate video. So let's say if we are applying the same input voltage to this V1 and V2, then the difference between these two voltage will be equal to 0, and at the output we should get a 0 volt. Likewise, when we are applying a different input voltages V1 and V2 to this op-amp, then at the output the difference between these two voltages will be get amplified by certain amplifier gain. So this common mode rejection ratio basically defines how well the op-amp is able to reject the common input voltages that is being applied to both its input terminals, and how well it is able to amplify the difference between the two voltages, and it is generally defined as the ratio of differential gain divided by the common mode gain. So for the ideal op-amp, the value of this common mode rejection ratio should be equal to infinity. So here is the list of different ideal op-amp characteristic. So the ideal op-amp has an infinite input impedance, infinite open loop gain, and infinite bandwidth and slew rate. And in this ideal op-amp, whenever the input is equal to 0, then at that time the output is also 0. And this ideal op-amp has an infinite common mode rejection ratio. But if you see any practical op-amps, they used to have finite input as well as the output impedance. Generally, this input impedance is in the range of mega ohms, while the output impedance is in the range of few ohms. Similarly, the open loop gain of the op-amp is not infinity, but it used to be in the range of 10 to the power 5 to the 10 to the power 6. Likewise, for the practical op-amps, whenever the input is equal to 0, at that time also you will get some output at the op-amp. Generally used to be in the range of few millivolts. That is known as the offset voltage, and we will talk more about it in the separate video. So here is the list of different parameters and the values of different parameters for the general purpose 741 op-amp IC. So now if you see the different op-amp ICs, they are optimized for the different parameters. So let's say if one op-amp is optimized for the very high slew rate, while the another op-amp is optimized for the very high open loop gain. And if you see some other IC, you might find that it is optimized for the very low offset voltages. So depending upon your application, you need to decide which parameter is critical for your application, and based on that you can decide which op-amp is suitable for your particular application. Now so far we have seen this op-amp in an open loop configuration. That means there was no feedback from output to the input. Now in the next video we will see what happens when we provide the feedback from output to the input side. So I hope in this video you understood the different characteristics of this op-amp. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.
Okay, so that's I think it summarize what I have explained in a more nice figure, I think. Okay, now let's see another video which I found and very interesting.
If you ever used ICs in your projects,
This is
then
the
you
AC.
might have noticed that most of them contain a triangle shaped component in their simplified schematic. Those triangles are called operational amplifiers, also known as op-amps. And since they are very common and useful for analog and digital electronics, I have used them before in a couple of different projects. So in this video, I will show you what op-amps are capable of doing and how to handle them properly. Let's get started. First off, you can get Opamp ICs in a dual inline package with either 14 pins that usually features 4 op-amps inside, or 8 pins that features 2 or only 1 op-amp inside. As an example, I will use the popular LM358 dual op-amp whose ground pin I connected to 0 volts and V plus pin to 12 volts, which is fine because it does not exceed the single supply range of the IC. Next, I apply the voltage of plus 1 volts to the plus inputs, aka the non-inverting input of the op-amp, as well as a 10 kilo ohm pull-down resistor to set the reference voltage to ground. Then I created a voltage divider consisting of a 5.1 kilo ohm and a 1 kilo ohm resistor in this constellation between the output pin and the negative inputs, aka the inverting inputs. As a result, I received a voltage of 6.1 volts at the output, which equals an amplification factor of 6.1. But why? Well, the first golden rule of op-amps gives us the answer. The output of an op-amp will always attempt everything to keep the voltage difference between the inputs at 0 volts. That means there needs to be the same voltage drop across R1 as the input voltage Vin. If we now add the voltage divider formula to this and the fact that the gain is the output voltage divided by the input voltage, we finally get the classical formula for the gain of a non-inverting op-amp. Such circuits can be used to amplify the signal from a sensor, like for example a PT100 temperature sensor, or the AC signal from an electret microphone. This one creates maximum voltage peaks of around 100 millivolts AC, which I can now easily amplify with a gain of 48 by changing the 5.1 kilo ohm resistor to 47 kilo ohm. But when we observe the outputs, we notice another problem. Only the positive AC voltage got amplified, because the output voltage swing is limited to the supply voltage. That means we would need positive and negative 12 volts to successfully amplify the complete AC signal, which I can demonstrate with my lab bench power supply. But since that is normally not an option, we could also add a DC offset to the plus inputs. This way the complete amplification does work to some extent, but because we are amplifying a DC voltage as well this time, we hit the 10.8 volt output limit of the op-amp pretty quickly. Why 10.8 volts instead of the 12 volts of the supply voltage? Well, there is no perfect op-amp. The ideal one would also have an infinite high input impedance and thus no input current could flow, which is not true. It would have an output impedance of 0, which means we could draw as much current as we want, which is not true, and the list goes on and on. But on the other hand, there does exist rail-to-rail op-amps that can achieve an output voltage which equals their supply voltage. And as long as you don't want to create precision circuits, such non-ideal parameters do not matter that much. But let's get back to the microphone amplifier. A more suitable circuit for this task would be an inverting op-amp. In this constellation, the plus input is connected to ground, which means the minus inputs must have a voltage potential of 0 volts as well. And since the second golden rule of op-amps says that the input draws no current, the current through R1 must be the same as through R2. This results in the classical formula for the inverting op-amp circuits. And by connecting the plus input to a DC offset voltage instead of ground, we can amplify the microphone AC signal completely without amplifying any DC voltage. The output signal can then be connected to a speaker, but just like I said before, because of the small maximum output current, the sound is almost unhearable. The last important rule when working with op-amps is that when no feedback is attached between the outputs and inputs, the output will either jump up to the maximum output voltage when the plus input has a higher voltage than the minus inputs, or in reverse, the output will jump down to the minimum output voltage when the minus input has a higher voltage than the plus inputs. The reason is the high open loop gain of the op-amp, and such a configuration is called a comparator. And there also exist separate comparator ICs that achieve a faster response time than the average op-amp. And with those three golden rules in mind, you can understand and build constant current sources and loads, voltage followers, integrators, differentiators, inverting, non-inverting, difference and summing amplifiers, Schmitt triggers, and the list goes on and on. As you can see, it is a versatile component and there's much more to say about it than what I just presented. But that is a subject for another video. Until then, don't forget to like, share and subscribe. Consider supporting me through Patreon to keep such videos coming. Stay creative and I will see you next time.
Okay, I think those two videos are very interesting. It shows theory and then how actually you can evaluate, you can see the performance of the op-amp. Okay, this semester I will give you all one project based on op-amp project. Like in the circuit theory, you were working with frequency analysis. This semester, we make it short for the frequency analysis, so much that we have done for the frequency analysis. So this semester we will explore more on the op-amp circuit. But later on, I will give specific tasks for the project, and those projects will be in groups. Okay, so let's come back to the lecture notes. Okay, based on the videos, in fact from my previous slides, I have mentioned an op-amp can be made into many applications. So, and also depending on the arrangement, you can make the op-amp either inverting amplifier.
Doctor, cannot hear your sound.
Doctor, you have mute yourself.
Okay, sorry, I was talking alone then. Okay, so let's move on with the many different kinds of op-amp application. So first, the basic principles of the nature of the output, whether it is inverting or non-inverting, depends on where you apply the input. Whether if you apply at the inverting terminal, you will produce an inverting amplifier. If you apply the input at the non-inverting input, you will get non-inverting amplifier. Okay, so here basically the inverting amplifier, when you have V1 applied to the negative input terminal, the inverting input, you will produce VO is equals to the RF divided by R1 multiplied with the value of your V in, which is V1 here. And in terms of the shape of the signal, for example, if you have a few millivolts AC of the input, and if you apply RF at few different values of the RF, you would have RF when your RF is 33 kilo ohms, okay, compared to when you use RF 75 kilo ohms, because in the output equation, output is equals to the gain times the input. So RF in the top of the equation, so it is linearly associated with the RF. So the bigger the RF, the bigger the signal output. So basically, how this would be the rough shape of the output signal. But because you apply the input at the inverting input terminal, the output will be opposite to the input in terms of the phase difference. Here you see the first phase would be positive. During the positive phase, the output will be negative phase. But the amplitude will be depending on the value of your RF. So if you want to make a variable gain, if you use a potentiometer at the RF, when you tune up the RF, you increase the feedback resistor, you will increase the output gain. If you reduce the potentiometer, you will reduce the gain also. Okay. In the arrangement of the inverting amplifier, the inverting, the non-inverting, the plus V plus is always grounded, and RF will determine the amount of the gain. Okay. For the non-inverting amplifier, okay, instead of putting the V in at the negative terminal, we now put the V in at the positive input terminal. Okay, and your RF is actually connected to your negative input terminal. Okay, and again, if you use the voltage divider rules, V1 is equals to R1 divided with R1 plus RF times VO, and if you rearrange, you will get the ratio VO over V1, which gives you the gain. The gain now becomes R1 plus RF over R1, that gives 1 plus RF over R1. So basically, the gain of a non-inverting amplifier now become 1 plus RF divided with R1. And because RF over R1 is normally a huge number, 1 does not affect very much. For example, if you have a gain of 100, 100 plus 1 is 101. Not much difference between inverting 100 gain and non-inverting 101. Okay, so the additional of 1 is not making a big difference. Okay, and this would be the equivalent circuit for the non-inverting amplifier, where you have V1 applied through here, and VI is actually between this point. And you measure a VO across the R1 and RF. So this VO is actually the voltage divider. Okay. And for a unity follower, you apply, you connect V plus input terminal to ground, and you simply short circuit the V minus to the output terminal. So that would give the gain is equals to 1 because the gain is VO over V1, and this will be your AC equivalent circuit. So whatever input you give to the Opamp, you will see at the output. So that makes a voltage follower or unity follower. And normally follower circuit is used for buffer circuit. And just want to delay the circuit without any loss of amplitude to the input. No amplification, and the output only follows the input. This circuit is useful for circuit isolation applications such as buffer. So normally a buffer circuit is present in instrumentation amplifier, for example. So here, if you have two Opamp, and you have V1 here, this V1 is applied to the first Opamp on the top, and V1 also is applied to the second Opamp in the bottom. And this one will be connected to the output of the second Opamp, and this one output to the first Opamp. An input signal can be provided to two separate outputs. The advantage of this connection is that the load connected across one output has no or little effect on the other output. So in this range, this first Opamp does not affect the second Opamp. You apply V1, so VO2 will be V1 also, same as VO1. But the input here is not affecting the output here, because this VO1 and VO2 will be applied to sub-circuits. So this buffer is useful so that you do not want to affect the next circuits, the consecutive circuits, following the VO2 and VO1 here. Okay, the summing amplifier normally works in the arrangement of the inverting amplifier, where for the summing amplifier, the positive input terminal of the Opamp is grounded, and you apply V1, V2, V3 to the negative input terminal of the Opamp, and VO is actually the sum of V1, V2, V3 that has been amplified. Okay, and for this circuit, the equivalent circuit, AC equivalent circuit will be like this, where you will see you have R1, R2, R3. They are all in parallel, and here you have virtual ground, and because the Opamp has a high input impedance, the multiple inputs are treated as separate inputs, and you will have the gain VO is actually R1 times the gain, like V1 times RF over R1 plus V2 times RF over R2 plus V3 times RF over R3. So each resistor here will give its own section gain. And the overall output VO will be V1 amplified, V2 amplified, V3 amplified. So that's why it's called summer summer circuit, where a summing amplifier actually sums up the individual voltage applied at the inverting input terminal. Okay, because VO is actually IF times RF, but the IF here is coming from individual current that pass through R3, R2, and R1. So, senang cerita, when you see a summing amplifier like this, each individual resistor connected to the voltage applied will determine the section gain. So in other words, you have 3 sub gains of this amplifier. Each input adds a voltage to the output multiplied by its separate constant gain multiplier. So the ratio RF to the R of each section is called the constant gain for that section. For the op-amp can also be made as an integrator, okay, where the integrator, when you include one capacitor in the feedback region, and you will make the behavior at the output like an integrator. Okay, because the non-inverting input terminal is grounded, V plus is 0. Your V negative or the V inverting input terminal is also 0 because of the rules. No current flow through the input terminal and no difference between two input terminals. So when V plus is 0, V minus should be 0 also lah. Okay, and therefore I that pass through this resistor R is now the difference between V in minus V divided with R, and that gives you simply V in over R. So the I that pass through the capacitor C, IC, is actually equals to C dV dt, and if you differentiate this one, dV dt is simply the value of the differentiation of V out minus V in, V minus divided over T, and that will gives you the value of C is actually dV out over dt. So you will have IC is a response of decay due to the presence of the capacitor. Okay, you can also make an op-amp an integrator. Integrator means you add up together IC plus IR must be 0, so that C dV out over dt plus V in over R is equal to 0, and dV out is simply 1 over RC times V in dt. So that makes V out is equals to 1 over RC, the integration of V in dt plus V out initial value. So when you give a square voltage, the output will be a triangular voltage. So in other words, the input signal is integrated at the output. And this integrator is normally used in low pass filter circuit and sensor conditioning circuits. For the differentiator, you have input of triangular waveform, the output will be in the rectangular waveform. The differentiator is always opposite to the integrator. So the differentiator opposite to integrator, integrator opposite to differentiator. Okay. The integration operation is one of the summation, summing the area under the waveform or curve over a period of time. Because of the square section, some of small region under the square wave, when you go from this point, move along, this area under the curve, area under this square will be increasing. So that's why you will have a line that is increasing. At this point, that would be the maximum value. But because the square wave goes to 0 here, the area under the curve at the region when it is 0 is 0. So you will have a jigsaw waveform. So you have increasing, and then up to this region it drops 0, and then it will rise again. When the phase is negative, you will have the opposite direction of the line here, slanting line. Okay. At DC, capacitor becomes open, and to make the Opamp working as an integrator, you need to introduce a feedback resistor in parallel to capacitor in the feedback path of the amplifier, Opamp. So when you have only one C, like R1 and then C and then VO, that circuit is a differentiator. But when you add R2 parallel to the C, you are making it as an integrator. And R2 must always be higher than R connected at the V in. Okay. The output voltage saturates to provide the closed loop gain at DC, and additional resistor is connected parallel to the capacitor. Okay. You can also make summing integrator. If you introduce one capacitor here for a summing amplifier, the circuit becomes summing integrator. And the summing integrator have the equation VO is equals to 1 over RC summation of integration of V1, V1, V2, and V3. Only when you have R capacitor in the feedback path. If you have a resistor here, the circuit will become a pure summing amplifier. But when you have a capacitor in replace of the RF, you will have it an integrator instead of summing amplifier. The differentiator, you place the capacitor at the input side, and you retain the RF at the feedback path. And the differentiator, similar, the rules here, when you connect V plus non-inverting input terminal of the Opamp to ground, current will not flow into the Opamp. So therefore, you will produce IC is equals to C dV/dt, and you will have IC is equal to C dV in dt. And I that pass through this resistor is equals to V out minus V V inverting input divided with R, and it is the value of V out over R. So the current that passed through the resistor is simply V out divided with the IR there. And IC plus IR is equal to 0, and V out is negative RC dV in dt. So you see in most of the arrangement, or almost all circuit connection, it is always applied, V in is always applied at the negative input terminal. The input signal is differentiated at the output and sensitive to noise due to the op-amp's high AC gain. And this differentiator is commonly used in high-pass filter circuits. Then you can have multi-stage gain amplifier. For example, if you have here inverting amplifier A1, second inverting amplifier A2, third inverting amplifier 3, A3. So the total gain of this circuit, because the circuit is cascade one after another, the total gain will be the amplification of overall, where A total, A is equals to the first amplifier gain multiplied with the second amplifier gain multiplied by the third amplifier gain, A3. And for each of the amplifier, okay, the first one is connected to the inverting, non-inverting terminal, and R1 here is connected to the negative input terminal. But for this one, you have connect V plus to 0. Here V plus to 0. So A2, this is inverting amplifier. This is non-inverting amplifier. So the first one will be 1 plus RF over R1. Whereas the gain for the second amplifier and the third will be the same. Okay. Output of the first stage amplifier becomes input to the second stage. And the output of this one becomes input to the third stage. Okay. You can also have another arrangement like this. Instead of cascade, you have parallel connection. And you apply V in to this terminal, which is connected to the inverting input of the second op-amp. But this one connected to this terminal, and this one connected to this one. So you have to evaluate individually. And if you notice, this one arrangement as parallel. A1 will be because you apply negative terminal R1, and A1 is the inverting with inverting gain. Sorry, there was a call coming in. I had to answer the call. Okay. So much interference. Okay, where I was. Alright. Okay, the multiple stage gain in the arrangement of parallel. Okay, the second amplifier A2 is also inverting. The third is also inverting. Only difference is value of R2, R1, R2, and R3. You have the same RF. This one different values. That makes individual stage of the op-amp becomes different gain. Okay, so when you have A1, A2, A3, these values, the overall gain will be additional to it. Total gain, no, you have individual gain. VO1 will be based on this gain. VO2 will be different gain. Unless you connect VO1 and VO2 to another amplifier, or maybe another amplifier here, then the overall total gain will be different. But for this one, there is no total gain here. You only have stages gain. Okay, now let's consider the real op-amp. In practical, the performance is slightly different compared to the ideal situation. The ideal op-amp versus the real op-amp. In the ideal situation, we have infinity gain, infinity input impedance, very low output impedance or zero output impedance, and zero common mode gain. But in reality, because of the BJT and MOSFET transistors within the op-amp, it restricts the infinity theoretical value. So that makes voltage gain is normally in the range of 10 to the power of 5 to 10 to the power of 9, depending on the op-amp itself. For example, you have 741, slightly different from LM 358. You can have other common multi-purpose op-amp. The input impedance, instead of infinity input impedance, if the amplifier is using a purely BJT transistors, the input impedance can be around 10 to the power of 6 ohm, which is around 1 mega ohms. If the op-amp is made of FET transistors, the input impedance is higher for FET. It can be 10 to the power of 9 to 10 to the power of 12 ohms. But for output impedance, it's only in the range of few hundred to about 1 meg ohms. The common mode gain, although in the ideal situation, common mode gain is 0, but in reality, in practical, the common mode gain will be a small number in the range of 10 to the power of -5, which is about few tenth of micro value, 0.00001, for example. So it's not 0, but it is very small number, and there is some gain. So the characteristics of the ideal op-amp are independent of temperature and supply changes. But in practical, the supply voltage, the temperature will influence the performance of the op-amp, because PN junction is affected by temperature. But when the circuit is operating for a long time, current flow within the circuit can cause rise of temperature. So the performance of the op-amp also change a little bit, especially if you have a very big current. It will alter the behavior of the op-amp after some time. Okay. Now, important factor for the op-amp is the DC offset parameters. So an ideal op-amp, when both inputs are zero, the output voltage should be zero. However, for a real op-amp, there is a small voltage DC at the output, and this DC voltage is referred as the DC offset voltage. So we have to apply this DC offset to make the output become zero. That's why we call it DC offset. So the voltage offset occurs due to the input bias IB and also to the input offset voltage VIO, and also due to the current offset voltage. So there are many factors that cause the offset DC voltage. The input bias current, when you have the IB plus IB minus, theoretically an op-amp should have an infinite input impedance and therefore no input current. But in reality, there will be small currents DC flowing at the input terminal, and the average of the two input currents is called the input bias current. So you have IB average, IB plus is equals to IB plus IIO, average of it, and IB minus is equals to IB minus IIO minus the average. And the total input bias voltage is the average of the two. IB is the average between IB plus and IB minus. IB may cause a voltage drop across the resistor of the feedback network, bias network, or source impedance. Typically, input bias current in an FET type op-amps is lower than that of the BJT type op-amps. And FET type op-amps has higher impedance, higher input impedance, if you compare from the table in the previous slide. Okay. The input offset voltage, VIO, the op-amp output should be zero when the input is zero, but this is only in the ideal situation. In reality, the input stages of the op-amp is not balanced. Okay, you will have a VO offset. When you apply here, when the input terminal is not grounded, you have R1, RC here. You will have V offset is equals to V input offset multiplied by R1 plus R2, R1 plus RF divided with R1. And the VIO is the amount of the voltage that must be applied to one of the input terminals to zero the output. So you have to adjust, you apply VIO, V input offset, to make VO here become zero. So before the op-amp works, you have to adjust by giving V input offset, VIO. And this VIO is because of the presence of, because of the non-ideal situation. Okay, and V plus is actually VIO. V minus is R1 over R1 plus RF times VO. And VO is actually VIO. And therefore, your VIO ni is actually the multiplication of VIO times R1 plus you know the value of your R1, your RF. So you just apply some amount of voltage. Normally this VO offset is a small value to adjust so that at the output becomes 0. So once your VO is 0, your op-amp is already set. So then it can change, it can amplify the signals according to what you want. Okay, an example of calculation for to calculate for the required offset voltage. So given a circuit with this one, you have RF equal to 150 kilo ohms. R1 is 2 kilo ohms, and you apply V in at this terminal, at the inverting input terminal. The non-inverting input terminal is grounded. Calculate the output offset voltage of the circuit below. The op-amp specification sheet lists VIO is 1.2 millivolts, meaning that in order to make VO equals to 0, you need to apply V input offset 1.2 millivolts to make the VO becomes 0. So VO offset is actually equals to VIO times R1 plus RF divided with R1. So RF you are 150, R1 is 2 kilo ohms. So you plug in the value. The VO offset should be 91.2 millivolt. So you need to apply this VO, or you don't apply, you will see an offset of 91.2 millivolts. And because of VIOU is 1.2 millivolt. So how can we reduce the output offset voltage? One way is you connect a resistor, a potentiometer in the output side. There are two. The first way is using an offset null input pin. The offset null is connected at the leg number 5 of a 741 op-amp, and you adjust the potentiometer until the voltage is 0. So the output offset voltage due to input offset current IO, if there is a difference between the DC bias currents both inputs, then this also causes an output offset voltage. The input offset current IO is specified in the specifications for the op-amp, and you will have as if there is a voltage drop across here, and this voltage drop is actually due to IB times R1. For the positive terminal, the voltage drop is due to IB times RC. And VO plus is equals to IB plus times RC multiplied by 1 plus RF divided with R1. And VO minus is equals to IB minus times R1 times the inverting arrangement. Negative RF times divided with R1. So VO offset due to the IIB plus and IIB minus is equals to IIB plus times RC multiplied by 1 plus RF over R1 minus IIB minus R1 times RF over R1. So the output offset voltage due to the input offset current can be defined as the difference between IIB that is present at the input terminals of the op-amp. If you assume R1 equals to RC and RF is far greater than R1, then our VO offset is equals to IIB plus multiplied by R1 plus RF minus IIB minus RF, and this will give you the equation there, so that your VO offset due to the IIO of value is simply the value of IIO multiplied by RF. And the total offset due to VIO and due to IIO, op-amps may have an output offset voltage due to both factors, V input offset and I input offset. And the total output offset voltage will be the sum of the effects of both. So therefore, VO offset is simply VO offset due to the VIO plus VO offset due to the IIO. And the op-amp specifications, the frequency parameters. An op-amp has a high gain, wide bandwidth amplifier, and this operation tend to be unstable, oscillate due to the positive feedback. And to ensure stable operation, op-amps are built with internal compensation circuitry, which causes the very high open loop gain to diminish with the increasing frequency. And this gain reduction is referred to as the roll-off value. In most op-amp, roll-off occurs at a rate of 20 dB per decade, or the value of 6 dB per octave if you consider twofold. But this one, consider tenfold. dB is 10, 20 dB is roll-off based on logarithmic 10, whereas octave 6 dB per octave is roll-off when you consider twice, or logarithmic to the base of 2. Okay, op-amp specifications, frequency parameters, and the specification of op-amp voltage gain, V voltage gain, where AVD is the voltage differential gain, is always given by the manufacturer based on the specification or data sheet. And to reduce the voltage gain, feedback resistors are connected to the op-amp, and the gain can be called as closed loop voltage gain. Okay. Unlike the open loop op-amp configuration, the addition of the feedback resistor to the op-amp improves the op-amp circuit by means of improving the stability of the op-amp voltage gain, increasing the input impedance, reducing the output impedance, and improving the frequency response. This is the gain versus the bandwidth. The op-amp has increasing frequency, the performance or the gain will reduce. I think I stop here and we continue, and I will post the many videos regarding op-amp application that helps you understand how concepts of many different application of Opamp. So until we meet again, so thank you for your attention. Thank you for your time listening to my lecture. Okay. So good luck for your e-test tonight. I will also have another